And am I audible? Like any problem from my side? Hello.
Yes, sir. As I told you, sir, there's mic issue in that catalog, sir. They follow you, but cannot speak to you, sir, because there's a mic issue in the catalog, sir.
All right, fine then. So if that is the case, let me teach you the today's session that I want to discuss something else regarding the simulations part, some more technical things. So what shall we do today? We shall try to simulate the airfoil today. We will learn how to model the aerofoil and what is an aerofoil. We will see those details, and then uh, we will look into how to model the aerofoil and how to simulate that. Those are the things we will look into this today's session. Those who completed the job, they can give the drag values of Reynolds number 20 and 50 in the chat box in the meanwhile. And also please listen the today's lecture. I'm recording that. Fine. So let's continue for the today's session. Just a minute, I'll share my screen. I hope my screen is visible to everyone. Aman, if it is like if you can interact with me, that would be better. At least if the others don't have any mic, so that I can understand my lecture is continuous and going smoothly. At least it is reaching to all. I feel like that. Is that possible, or anyone who can interact? That would be greatly appreciated. Okay. If you are able to see my screen, can you all please raise your hand? 1, 2, 3, 4. Okay. So just a second, guys. I will. Sorry for the interruption. So if you are able to see my screen, today I would like to discuss what is this aerofoil. So aerofoil means it is the shape. Generally, we consider it is in a two-dimensional shape. So it is a pure curvature which is continuous everywhere. In the basic sense, I hope you all know uh, at least some details of an aircraft. So if you are seeing in any aircraft, we generally say this particular part, this part. is the wing of an aircraft. Okay, wings are the key parts which are generating the lift for the entire aircraft. Okay, so specific to the wing, if we focus and if you cut any cross section of the wing, that means the way that the plane is designed here. If you cut the cross section of the wing like this, you will see the shape of the aerofoil. Okay, this is how the shape of the aerofoil looks like. So this is common for any of the aircrafts. Maybe the shape of the aerofoil differs, but the terminology is same. All the wings has some shape at this cross section if you cut the wing in this particular pattern. Okay, so to see the aerofoil, here we see the aerofoil in the dotted lines. Okay, if you want to see from the side view also, for this is an aircraft. Okay, so if you see the wing of an aircraft from the side view, we say this particular thing is an aerofoil, the cross section. Okay, so this aerofoil is generating the lift on the upward direction. Okay, and there are certain terminologies corresponding to this aerofoil that one should learn. You can also see how this aerofoil is actually working. If you have an aerofoil here, the aerofoil has a capability to, or it is designed in such a way that it can generate the high pressure at the bottom surface and it can generate the low air pressure on the upper surface. Because of this high and low pressure differences, it is able to create a net upward force. Okay, so this is the basic idea of why we are generating the lift and what is the importance of aerofoil. Okay, and few more characteristics of an aerofoil are show you the characteristics. Yeah, this is one. So we say the let me find out the correct one. Yeah, this is very good. So for the aerofoil, if there is any aerofoil, generally there are few common parameters like the basic main parameter is the length of the aerofoil. Length of the aerofoil means the extreme leading portion we say as a leading edge. Okay, extreme leading portion is called leading edge, and the extreme trailing edge we call as the trailing edge. Okay, so the distance between these two extremes we are saying as a chord length. Okay, the distance between these two extremes is called the chord length. All right. Okay. So then, and the thickness. If you are cutting the planes vertical to the chord line, okay, just assume that you have an airfoil shape automatically generated by somehow. Take it as granted this shape is generated by somehow. Now, if you want to understand, measure the thickness, you need to draw the lines vertically to this chord line. Chord line is now horizontal. If you draw vertical lines perpendicular to this chord line at every instant, you will see the thickness of the aerofoil. That means this point to this point, it is varying constantly from the leading edge. Not constantly, it is varying with some function from leading edge to trailing edge. Okay. If you take the mid portion of the thickness at everywhere, if you take the mid portion of the thickness, that mid portion is contributing for the camber line. Okay. These are the key parameters that an airfoil consists of. Okay. So, and then why we are looking at the aerofoil? What are the important parameters that regarding the forces that airfoil consists of? An airfoil can generate a net resultant force. Net resultant force can be in any direction, but usually the way the airfoil is designed, it is usually in this particular direction. Okay, if you take a first quadrant, it lies always in the first quadrant, the resultant force. The resultant force is because of the flow passing over the airfoil. Because of the flow, this is the flow direction, and your airfoil is like this at an angle, some angle. Okay, because of that angle, you will see some resultant force on the airfoil because of the flow and the shape of the aerofoil. Okay, and if you resolve the directions of the resultant force in upward and horizontal way, exactly upward and horizontal way, you will see a more amount of force in the upward direction. That force we call as lift, which is the crucial force that lifts the aircraft upward. Okay, and this force is the drag force. This drag force that pushes the aircraft in the backward direction. To overcome this drag force only, aircrafts or any aircraft or the flying vehicles should need a propulsion power. That means some jet engines or any thrust generating system. Okay, so to overcome this particular drag only. Okay, and then what is this angle of attack? Angle of attack is such a terminology that we already know what is a chord line. So angle of attack is the angle between this particular chord line and the flow direction. This is the flow direction, and this is the angle of a chord line. Chord line is now you can see tilted instead of horizontally placing. Now it is tilted with some angle with respect to the relative wind. So these angles from the relative wind to the chord line angle is called angle of attack. Okay. So center of pressure. Center of pressure, we generally say it is a terminology where your resultant force is acting. If you have the aerofoil from this portion to this point, your resultant force does not necessarily to act at a constant location along the chord line. It may vary to forward and backward, and it may act at the leading edge, it may act at the trailing edge. So generally, the resultant force acts at this particular location. Okay, we will see what is that particular location and how to understand the resultant force location. Okay, that means if I'm saying a cylinder, there is a cylinder. Uh, we generally consider these forces are acting at the center of the cylinder in such a way. If there is an aerofoil of this kind of shape, looks like irregular kind of shape. If the aerofoil is acting like, how do you understand where are the resultant forces are acting? If you don't understand where the resultant forces are acting, you cannot counteract those forces or you cannot balance the forces. If you don't balance the forces, your aircraft will will be imbalanced and it may chances to destroy, collapse also. So you need to understand where your forces are acting and how much of forces are also acting. Okay, this part is clear. If clear, please raise your hand. Any network issues in the lab? I see very few students are available from the lab side. Or there
Uh,
are not. How many are
they
there?
cannot talk to me because yes, sir.
I understand, but how many people are there in the lab right now? Or
Uh,
listening from the
five five people is there, sir.
five people in the lab. All right. So that's fine. Um, so now we understood what is an aerofoil, right? If that is clear, let's look at some more details of an aircraft for an aerofoil. Okay. If you have an aerofoil like this, okay, this is not a symmetric aerofoil. Let's take a line, horizontal line, x and y axis. This is a horizontal line. Okay. And this is a vertical line. You have y-axis here and you have x-axis here. Okay, if you draw your aerofoil if your aerofoil shape is such a way that if it is symmetric on the both upper half, this we say as the upper surface, and this is the bottom surface. Okay, so if your aerofoil is symmetric on both upper surface about the x-axis or about the chord line, that we say as a symmetric aerofoil. Okay, if it is not symmetric, that we call as cambered aerofoil. Let's not dig into the details of this cambered aerofoil. Let's stick to the particularly to the symmetric aerofoil. So now we are dealing with the symmetric aerofoil. That means the surface or the curvature is symmetric about the x-axis on both upper surface and the lower surface. Okay, this is a symmetric aerofoil. So these details are done. All right. Okay. So now we need to understand aerodynamically, it is already written in very well in several textbooks or a kind of Bibles, you can say. People usually say the terminology, or you can say it's well documented uh, literature or well documented studies or a Gita kind of thing that you can understand. So all these things are well documented about the characteristics of an aerofoil. So how do you understand the characteristics of an aerofoil? So if you have an x-axis and a y-axis, so this is not an x-axis. Let's say this is an alpha axis. This is an alpha axis, and this is a lift force. Okay. Uh, let's say let's say it is a lift force. Okay. So now, what is this alpha? Suppose here in this figure, you place your aerofoil in such a way that the chord line is aligned to the x-axis, and assume this is your flow direction. So flow direction is also aligned to your chord line. Okay. In some way, you modified your aerofoil like this. And then flow direction is horizontal only. Flow direction is not changing. Let's assume the flow direction is horizontal only. Okay. So the angle between this horizontal flow direction and the chord line, this angle we say as alpha. Okay. The chord line, this is the chord line, and this is the flow direction. And alpha is nothing but angle of attack. All right. So alpha is nothing but angle of attack, and this is the chord line, and this is the flow direction. Fine. So now, what is actually documented in the literature or in the textbooks or in the clearly maybe the knowledge available on this aerofoil aerodynamics? So if you change your angle of attack in such a way, suppose my angle of attack is first initially at 0. Okay. What I already told you, lift is the force that acts perpendicular to the flow direction. This is the lift. And if it is this is the flow direction, then we say this is the lift force. The force acting upward and also perpendicular to the flow. This is the flow direction. Okay. If the flow direction, then lift should act in the perpendicular to the flow direction. So at 0 angle of attack, that means if there is no angle, can anyone guess what would be the lift value? So at 0 angle of attack,
So
you would,
for symmetrical, it is zero, subject value is zero. So
yes,
there is
exactly.
upper and lower surface.
Exactly, Aman. Very good. So at 0 angle of attack, you would get automatically the lift value is 0 because it is a symmetric angle of symmetric aerofoil. Okay. At the same way, if you slowly increase your angle of attack, you will see the lift also increases linearly with angle of attack. Okay. Up to a certain part. Up to say that certain part we say is called alpha stall. Okay. I'm not digging deep into this aerodynamics of alpha stall and everything, but I will just give you the overview of what is this alpha stall. So up to certain angle of attack, if you keep on increase this particular angle of attack, up to certain angle of attack, you will see a steady or linear increasing of the lift, and after that, you will see a fall, a drastic fall of the CL or the lift force. Okay, this particular portion we call stall. So increasing the angle of attack, you would get increased lift, that means more lift. But always increasing the angle of attack is not suggestible, because you will see a stall, a particular fall of lift after some particular angle of attack. That angle of attack we say generally as a stall angle of attack. Okay, this is how we generally get the lift. And also in the aerodynamics terminology, generally we don't say lift as a lift. We always try to say in a non-dimensional format. What is this non-dimensional format? So lift is a force in newtons, but we talk in a lift coefficient format. Lift coefficient, which has no units. Okay, how do you find this lift coefficient? Lift coefficient we generally write as CL, capital C, and if it is an aerofoil, there, let's assume this is for the capital L, but time's sake, as it is not a problem. There are some other terminologies that we can discuss later. So capital C and capital L, this we call as lift coefficient. Lift coefficient is nothing but lift by, that is force by, half of dynamic pressure. This is we say Q infinity. Okay, dynamic pressure into the area. Okay, let me not confuse you. I will give you the full formulation. That is lift by half into rho into flow velocity square. If rho is density and v is the flow velocity, the time square into surface area. Surface area is, if you are seeing the airfoil from the top view, what you will see? You will see the first chord length, okay, and the span. If you consider there is no span because it is, I'm saying in the two-dimensional way, you can consider it is a unit span. So the surface area is chord into span C1. So this is what we consider as a lift L by half rho p square c. This is what coefficient of lift we are saying. All right, fine. So these are the basic details of an aerofoil. Now let's look into how to generate an aerofoil in the aerofoiltools.com. If you have access to the Google, and like if you can do that easily. So how to generate an aerofoil? Let's see that. So first we need to get this one, www.google.com, and then go to aerofoiltools.com. So the website is airfoiltools.com. Okay. Then go to this NACA 4-digit aerofoil generator. Okay. You can ask me what is this NACA 4-digit aerofoil generator, sir, but it is now not an essential part for us. We can learn that slowly. Okay, fine. So if you want directly from the database, you can select from the database. Let's select the database. There are several aerofoils available in the NACA series, but the mostly commonly used aerofoil is NACA 0012 aerofoil. Okay, this particular third one. I hope you can see this highlighting one. So this NACA 0012 aerofoil. If you select that NACA 0012 aerofoil, you can see the plot, how the aerofoil is looking. Okay. Yeah. So this
So
is
these
how.
are the dimension of that airfoil section.
Sorry.
These are the dimension of airfoils.
These are the coordinates of the aerofoil. If you draw in the XY axis, you will get these are the coordinates of the aerofoil.
Okay, sir. Okay, sir.
Okay. So we can send this to an airfoil plotter, send to an airfoil plotter. So if you want to change any details, you can change the details like a number of points you require, or if you want to print directly on something, you can print it, or you can do some additional things for changing the properties of this NACA 0012 aerofoil. If you don't want to do any changes, you can directly get the CSV file coordinates of it, or also .dat file format coordinates also you can get. So for the time's sake, let's get the CSV file of coordinates. CSV file of coordinates is something like a file format, file extension that consists of all the coordinates. Coordinates means the points. X equals to 1, then what is Y value of these coordinates. Along with that creates the aerofoil. So let's download this CSV file of coordinates. If you click on that, you will see, you can see that there is a aerofoil downloaded in my browser. Airfoil coordinates. Okay. So these aerofoil coordinates are automatically stored in your downloads folder that you can copy it to your particular folder. And here what we need to do, let's open this aerofoil folder location, what actually consists of this CSV file, and then what we need to do for the process. So here you can see there are some details of your aerofoil that is saying about many details like what is the chord, what is the radius of leading edge, thickness, origin, pitch, degrees, everything. So these details are not necessary for us. What we need, we only need the airfoil surface coordinates. Okay, airfoil surface coordinates x in mm, y in mm. So the default units that website has, the coordinates of airfoil x and y mm. So if you plot these things, so let me plot these airfoil surface coordinates, you will see the aerofoil. Clear? Understood?
Yes, sir.
Okay, I hope this is clear. So then you got the aerofoil. So these are the points we need. Okay. So if these are the points, can I use directly these points to create an aerofoil in our design software? That direct answer is you cannot directly import these coordinates into your design software because your design software cannot understand these are the points. You need to create the coordinates in such a way that there should be a third axis because we have three axis system. It's a Cartesian coordinate system. There should be three axes, x, y, and z. So create a z axis also. Okay. And then give the numbering of 0, 0, 0 for all up to the last. So like this. In the z axis also, you should add the zero coordinates. Then it understood, the software can understood that we are going to design something with these kind of coordinates. Okay. So far we use the design modeler as our design software, but I suggest if you are experienced with any other design software, ANSYS design modeler has the capability that you can import any design that you generated in any other CAD software into the ANSYS design modeler or ANSYS modeling software. So this is a flexibility so that if you are very well experienced with the tools, with the other design software, there you can design with your flexibility and you are applying your skills if it is a complex model. So for me, and this design software, the design modeler, what we've seen already, it is quite flexible, but it is more beneficial for in terms of 2D or handling the surfaces, but it is not completely handy for me, specifically for my saying, because I generally use a more 3D complex, very complex geometries. So I always prefer SolidWorks as my design modeler. SolidWorks, I will create the geometry, all the details in the SolidWorks, and then I import that geometry into the design modeler to save my time and flexibility in designing. So this time also, I hope you all know any other CAD softwares. I believe I will show you today in the SolidWorks. You have many tutorials also to do the same process in doing the design modeler or in doing the CATIA or AutoCAD, any software. Okay. So for that, I believe you all have the SolidWorks also in your system. You might have been practicing that. If it is the same case, then it will be very easy for you all. So that's not an issue. So what we need these kind of coordinates in X, Y, and Z format. And also what we need, let's make these things scaled up. I mean, scaling up means if you can see X is in 100 mm, but I want X is in 1 mm or something. Okay. So why I'm doing this, you can understand it better later on. So right now, if you want to scale it, I will say 100 by 100. That means whatever this value in the XMM, I'm scaling down to 100 mm. And let me drag this part. You can fill it if fill is working for you. Okay, not this one. Okay, now I just scale the X values. That means 100 mm equals to 1 mm. I want to convert, so I converted it. In the same way, I want to convert Y by 100. Y also to scale down to 100. Okay. Like this, I want to scale down. So I scaled Y also. Z I need to scale? No need because Z is already 0. So you can say Z is 0. So Z also we have values ready. And one more final step we need to do is we need to make all these digits up to 4 pi levels. So what is this 4 pi levels? You can see some values are decimal places up to 3 decimal places, some are 2 decimal places, some are 1 decimal places. This is not looking reasonable because um, having constant decimal places for all the numbers that you're seeing here, that would be better. So you see this particular number is having 0.061, that is 3 decimal places. The above numbers are having 5 decimal places. So to make all the decimal places consistent, you can use this particular format, that is increase decimal places like this. Now you can see I have increase or decrease. I can increase or decrease here like this in Excel. So at least up to 4 5 decimal places are good. Let's take a 4 decimal places. So all the numbers that I am seeing here are now in the 4 decimal places point. Okay. So what we need to do after this, after generating these points, just copy these particular points that you generated just now. These are the airfoil coordinates. Copy these things and then go to your working directory and create some text file, text document. That is, you can right click and go to the new and go to the text document. Like this, you can do that. If you go to the text document, you can name it as an aerofoil. Okay, aerofoil, and open that text document. Just paste these coordinates. Just copy and paste. Okay, just copy and paste these coordinates. You will see these kind of coordinates that are already saved in the airfoil. So in the same way, I also saved the coordinates as an ACA 0012 airfoil. Before that, you can see these are an ACA 0012 airfoil coordinates. That means the same thing what I have already generated that I stored previously. Fine. Up to this step, clear for everyone? Is it clear? Like at least you understood the steps. Follow up. You can look into
Yes, sir.
the recorded video later on, and you can follow it up. But this part, I hope you everyone understood. If you understood, you can just raise your hand. Yeah, fine. I hope you all understood. So now we are going into the design modeling software. That is, let me use the SolidWorks as the design modeling software. Then we can use the remaining software for our today's work. So for that part, I request you all, let's take a 10 minutes break and we will join this session exactly at 3:33. Sorry, 3:33. Yes, exactly. So take a 10 minutes break and we can join once again. 3:33.
Sir, we have to do something, sir.
We should take 10 minutes break, Aman, nothing to do.
Okay, sir.
10 minutes, we shall join around. Or in the meantime, if you are interested, you can do this work, do this exercise. Download your coordinates of NACA 0012 and store in your file in these 10 minutes. We will get back.
Okay, sir.
Yeah, thank you. Sorry for the delay. You are all available here. Am I audible? Hello,
Yes, sir.
Aman. Okay.
Yes, sir.
Yeah. Yeah. Sorry for the delay. So let's start with the this one. SolidWorks modeling of NACA 0012 aerofoil. So what we are going to look into is we are going to now design the a SolidWorks model of for simulating this NACA 0012 aerofoil. So for that you definitely need the SolidWorks. Just a second, guys. Just a second. Sorry for the interruption, guys. Really sorry for it. So So let's take a new component in the SolidWorks domain. Let's take a new part. So this is the new part. I hope you know this, how to take a new part in the SolidWorks modeling. And then the first task is we need to import the geometry, the curvature details, the NACA 0012 curvature details into this particular software. So how to import that? So if you want to import that, you just go to the this particular futures tab. You should be in the futures tab, and then reference and then curves, 3D this option, the curves option, and then use the option called curves through XYZ point. Okay, curve through XYZ points. So select this particular option. Once you select that, you can just now take the points by using this browse option. You will see this kind of a window. So then you can use the browse option. Okay, and then you can go to the directory where you stored your geometry files. Okay, if I stored your geometry, I mean not geometry files, the coordinate files. Okay, I stored the coordinate files here. But you see here in the drop down, it is looking only for the .sld crv files. But we also want to use the text files. We created only the text file. So you can use the .txt format also from this drop down. So select the .txt format. Only after selecting this .txt format, you can see there are two files. Okay. Only after selecting the txt file only, you will get the text files. Fine. So use the NACA 0012 file coordinates. If you want these file coordinates, I will share it to you, or else I already described the process how to generate these file coordinates. Okay. After generating that, after adding those files, you just click OK. Now the curve is added into our workspace or the graphics area, but we don't see any curves here. So what to do for that? If you just click the zoom to fit view, now you can see a smooth NACA 0012 airfoil curvature. Fine. This is how we need to create the NACA 0012 airfoil curvature in our graphics area. All right. After this, what we need to do? After this, what we need to do? We need to um, create the domain and face splits because we are going to do the structured meshing. So the first thing is we need to create the domain. Okay. On what plane we can create the domain? We can create the domain in the, let's take the front plane. So I'm taking the front plane and I will create the sketch on the front plane. This is the front plane and I'm going to the sketch on the front plane. So I will just convert these entities. I mean, this is the curvature in 3D. So I want to make this in the 2D curvature. So if I go to the sketch, I can extract that 3D sketch into a 2D sketch by using this convert entities. So I use this convert entities and select this curvature. So after this, now you can see it is now entered or created a sketch on my two-dimensional plane, that is a front plane. All right. Right. So if you want to like see the geometry clearly, you can find it out here. One problem in this particular geometry, that is, just give me a second, something is wrong here. Okay, maybe my pen is doing some mistakes here. So this is not the correct. All right. Yeah. So if you see your geometry carefully at the trailing edge means this extreme end portion. At this trailing edge, you don't see like a curvature, like a sharp trailing edge. But for our modeling, we always generally recommend a sharp trailing edge. So we need to do some post processing at this trailing edge. What I generally do, uh, I will create a vertical line here, which is for a construction purpose. That means this is my vertical line, and then I will transfer this line into. Okay, let's be before transferring. Let me trim the remaining portion. So I will just trim this additional portion. So go to trim and cut this trailing edge portion. Okay. So now add the dimension in such a way that at least 99% of your chord length should not be disturbed, because we cut a small portion at the trailing edge and remaining portion we keep it like constant. So this should be 0.99 because our chord length is 1 mm and this is 0.99 dimension. So 0.99 mm is safe. Only remaining amount length we cut from this trailing edge portion. So why we cut this? We want to generate a sharp trailing edge instead of this curvature. This curvature can make a problematic kind of things while we are modeling and matching the things. So that's why we cut this particular portion. And then now we will do the sharp trailing edge here like this. Okay. So this sharp trailing edge should be tangent to your curvature. This is your airfoil curvature and this is the sharp trailing edge. These two things should be tangent. This should be tangent like this, and this should be tangent like this. Okay. So these two things should be tangent first. After creating the tangent, we can make this particular line, this particular vertical line to construction. All right. This particular vertical line to the construction. Fine. Now you can see I created an airfoil with the sharp trailing edge. Okay. This is how you need to create an airfoil on the front plane. So now my airfoil sketch is ready. Any doubts so far? I hope this is all familiar to you. Sketching part and trimming and all these things. So after the sketching, what we need to do? We need to do create a domain. Let's take a rectangle first. So I will start my rectangle from the trailing edge. I will go up to here. Okay. The standard values are like this from the leading edge portion from the origin to the top side, which is generally 5 mm or 5 times this chord length. Okay, 5 times this chord length. In the same way, at the bottom side also. The same way at the bottom side also, it should be 5 mm. All right. And in the way It is generally wake means after the length behind the trailing edge is generally 10 c. Clear? All right. And the distance, we need to join this with the trailing edge. These two things should be coincident. Okay. So now this is a trailing edge part computational domain. I need to create a remaining computational domain also. So let me complete the remaining computational domain, then you can understand it much better. So what is the remaining part? I will take my origin for this arc here. Okay. And then we'll complete the front end as a C part. All right. Fine. So this one should be a construction part. So this is my aerofoil and this C circle section and the rectangle, the combination of C and rectangle. This is we can generally say as a C domain, C computational domain is my domain around the aerofoil. Okay, like the way we created the domain around the cylinder. This is my aerofoil and the C computational domain that we created around the aerofoil. All right. Yeah. So this is particularly done for creating a computational domain and the aerofoil. Now we need to make the sketch or surface from this computational domain. How to create the surface from this computational domain? So you just go to the search button and type the plane command. There is, sorry, not a plane command, surface. You can ask for surface. Okay, you can ask for the surface command. So you can select the surface. So, just a second. Surface. Planar surface, I guess. Yeah, the correct command is planar surface. So go to the command center and search for the planar surface. Planar, planar surface. Planar surface means it creates a surface in particular to the plane, restricting to the plane and using the boundary entities. Like the way we are creating the surfaces, or surfaces from the sketches and the design modeler. This command also behaves in a similar way. Okay, if you select your sketch, it automatically generates the planar surface related to the non-planar selection of open section. So open sections are there in our sketch. Let's edit that. So this is not required one actually. Preview. So planar surface. Okay. I still have somewhere open surface. Let me detect that. Open surface is something like you need to repair the sketch somewhere it is problematic. See any problematic surface here. Okay, so there is no problem in the sketch. We need to select it carefully. So this is my sketch and I use the planar surface option and then I selected my sketch. You can see now it is creating the surfaces and then click apply. So this is how you create the surface in a two-dimensional way. You see there is no thickness for it. All right, there is no thickness for this surface. So now what is our next job? Our next job is to create the blocks for creating the structured mesh, right? You already know why we are creating the blocks. So how to create the blocks? So for creating the blocks also, we have a principle of creating the blocks that each block should consist of a four faces. In such a way, we have to create the blocks. So how to create those blocks? So let's take a sketch on this particular plane itself. Okay, again, I'm drawing a new sketch for supporting my blocks and splitting the faces. So I need to draw the lines first that supports my blocking. So I will create a block here and here. Okay, and then I will create another block. One is vertical block and another is horizontal block. Okay, these two blocks are done. And one more additional block to preserve the shape of the aerofoil, I'm creating somewhere in the here from this part to this part. And this should be vertical. Okay. And the distance of this line from the leading edge should be 0.03. Sorry, 0.3, not 0.03. It should be 0.3. So these are the block sketches that we are going to create the blocks with the help of these sketches on the space. Okay, so exit it and use the option of split, SPLIT. Then you will find this particular option, split line. Okay, split line option is available. So use the split line option and select the sketches that you want to project onto the face. So I want to select these sketches and my face is this particular face. Okay, so I selected these two and click OK. Now you can see I have a blocks. I have a blocks clearly and it is a zero thickness, two-dimensional body. This step is clear, everyone? Understood? If understood, just raise your hand. We can move to the next step. Yeah. Ajoy, Priyanshu, fine. So, Necha, very good. So I hope you understood the commands. Here we are only used the three new commands, that is curve command, curve one 3D curve, and then surface planar command, and then split line, nothing else. And one more final step that we need to do is scale it up, scale the domain to, that means now the aerofoil chord length is 1 mm. For the sake of simulation purpose, I want to make it as a 100 mm again back. So take this as granted. Why I'm doing this, you can understand only after getting a good experience of the simulation. So I'm scaling it up to 100 mm based upon the origin. Origin is this particular origin at the leading edge, and I want to scale 100 times, uniform scaling. All right. Yeah. Now you can see my actual curvature is 1 mm. My curvature won't change. I mean, the first curve I took, that won't change, but my domain or geometry is increased to 100 mm, 100 times. You can see this is my actual curvature I imported, but after scaling, this is the complete domain. Clear? If that is the case, what is the next task we need to do is we need to save this in two formats. Save this geometry in particularly to the two format, where first format is NACA 0012 in a SolidWorks format. Okay, I already have that file, NACA 0012 SolidWorks format. You can save it as if you require NACA 0012 file 2. Okay, so you just save the SolidWorks format, that is common. Always everyone wants to save in that particular format. But additional format that generally helps to import into the design modular much better is go to the file option and save as. Use the save as option and select the Parasolid XT format. This one. The option format is Parasolid XT format. Okay, you select this option and then save it. Okay, now you can see in your directory there is something like NACA 0012 and the extension is not showing here. If you want to see the extension, right click and go to the properties. There you can see the application extension is .x_t. This is the Parasolid format. Okay, which is best for importing the geometries into ANSYS Fluent or the design modeler. So now our designing part is done. We have few more steps to do in the design part and proceeding for the structured mesh. All right. Okay. So what we need to do in the next step? The next step, let's open our geometry, our workbench. I have saved all the files in particular format. So this is the file I have been using for you all to for this tutorial sessions. So open your workbench and then import project was saved in the future version. Can I save it from okay, saved in the future version of the fine bench. Sorry. Just a second, I want to open my. So it is maybe looking very odd for you here. Let me change my resolution and I will open it once again. Just a second. This one. You are able to see my screen, right? Everyone?
Yes, sir.
Thank you. So now this resolution will be better. Right. So take a new geometry, not new geometry, new fluid module. This is the fluid module. So take a fluid flow fluid module, drag it and place it anywhere as you wish. Okay, and rename it Naga 0012. This is the maximum I can do. So this is my module now, fluid module I just loaded. So here I will do the geometry, meshing, everything I will do in this particular module itself. So now what I need to do first, I need to import the geometry. So right click and then select the import geometry option. Where you need to right click, select the geometry first and then right click and use the import geometry option. From this import geometry option, browse the geometry that we saved in a Solid XT format, that is NACA 0012. Okay, so select this option. After selecting it, you can see now the geometry got a tick mark, green tick mark. Okay, so that means it is imported successfully. So let's edit the geometry. Let's go to the geometry and we will see any discontinuities in the geometry or not. So right click and edit geometry in design mode. Let it open. All right. Now you are seeing, I said already the model is imported, but you can see a separate thing like import one. That means the model is yet to be imported. Model is ready, but not yet imported successfully. To import it, go to the generate option and click it. Now you can see the model, the same model that we just generated in the SolidWorks. All right. So this model, what we are going to check it now, any discontinuities. What is the rule for the block meshing? The rule for the block meshing is all the faces should have only four edges or the four boundaries. So if I select this face, there are four edges or not. This is one edge, two edge, three edge, or four edge. Fine. One, two, three, four. Fine. One, two, three, four. Fine. One, two, three, four. All right. One, two, three, and the small portion. You see, the small portion is four, and again one small portion, two and three, four. All right. So this looks all right. I don't find any breaks or any discontinuities or number of edges. But with my experience, generally the SolidWorks creates a problem here because we made a cut here and joined the trailing edge. So if you select the edges clearly, there you can see the breaks. Now can you see the breaks? This is my green line and there is a break here. It is not selecting this. This is one edge and this is two edge. But it should be both combinedly a single edge. Right, not like these two edges. Because this we did, it joined the trailing edge sharply in the SolidWorks. Because of that problem, it lost its continuity. In the same way, in the bottom line also. All right. So what we need to do now, it has this particular face has five edges, not four edges. So to solve the problem, select all these discontinued edges. Okay, select all these discontinued edges first, and go to the tools option. There you can find an option called merge. All right, go to the tools option and there you can find the option called merge. So select this merge option and then click apply. Fine. After clicking apply, you can just press generate button. Now you can see the those edges are joined automatically. No issue with that. It's joined. So now all my faces are having 4 edges. So now I'm ready for the block meshing or the structured meshing. So this is done. You can just save it. And now let's go to the meshing part. Okay. So click on the meshing part, right click and edit. These things all you know. I don't need to explain it again and again because I believe that you already did the cylindrical part. So let me open the meshing part. Then I will show you how to do the same meshing. The process is same that everything we did for the cylinder. This is the same process for airfoil also. Okay. So now my airfoil geometry is imported into the meshing. There, what I need to do, I need to select uh, face meshing first. So right click and go to the insert and select the face meshing. Okay. Face meshing, can select all the faces, what you just block. Select all the faces and click apply. So this part is done. And the second thing I need to select the size of the elements. So the element size, generally we took last time as a radius of the cylinder. This time I will take uh, 1/4 of my chord length. My chord length is 100 mm because I already scaled it in the SolidWorks itself. So I scaled in the SolidWorks to 100 mm. So now I'm taking 1/4 of it. That means around 25 mm. Let me see if 25 mm it is directly taking or not. So it is not taking like 25 mm. I should give the input of 0.025. All right. So 0.025 is the element size and face meshing I applied. And I also want to apply one more setting, that is edge sizing. Go to the insert and edge sizing. That means this is already you know better because I told you in the while doing the cylindrical. So apply the edge sizing particularly to the wall, only on the wall. So edge sizing for the edges. Select the edges of the wall. 1, 2, 3, 4. 4 edges you selected and apply. Okay, element size, because my chord length is 100 mm. I want to choose the element size on the aerofoil as say 1 mm. Okay, if it is 1 mm, I can use the element size is 0.001 and the behavior is hard. All right, fine. If that is the case, then you can click on the generate option. All options are set. Click on the generate option. Now, if you want to see the mesh, click on the mesh. Clear? This part is clear up to everyone. Like you can raise your hand if it is clear. Like meshing, modeling, geometry. I hope it is clear for everyone. If it is clear, you can just raise your hand and you can tell me it is clear. If not, if you have any queries, you can text or talk with me now. Any queries? Okay, I hope there are no queries from your end. So this is the part with the meshing. So there are no additional changes in your simulation. We can use the same simulation settings. But what we need to do, we need to calculate the Reynolds number first. So how to calculate the Reynolds number? Let me share my screen once again. Uh, what happened from your end? I hope everybody is available, right? Or you're facing any issues? Aman? So how to calculate the Reynolds number? As we already discussed, Reynolds number is RE equals to, Aman, is the screen is visible? Reynolds number RE equals to rho V D by mu. All right. So rho V D by mu. So what is this rho V D by mu? We already know what is, or we calculated the Reynolds number. Aman, are you there? Am I audible to you all? Priyanshu? Hello, am I audible? Hello, Aman or Priyanshu, can you text at least? Am I audible or something is wrong at your end? Or you can text in WhatsApp. Hello, Priyanshu, is there any network issue at your end? Hello, can you text me?